Hello, in this video I'm going to be teaching you about vectors and vector addition, okay, and we'll be using forces as an example. I think most of you, when you hear the word vectors, you will think, oh, vectors have magnitude and direction. And then you contrast this with scalars, right, which only have magnitude and no direction. If you can memorize this, then good, but do you know what does this mean and why is it important? Okay, so that's what we'll be exploring today. Basically, the idea of having both a magnitude and a direction, this is because certain physical quantities, for example force, the direction in which the force is pushing or pulling does matter very much. Okay, so for a very simple example, we can look at this diagram here that shows that this bus, right, has a driving force that's pushing it towards the left, but at the same time there is a opposing force, the resistive force, like from friction, from air resistance and so on. It's pulling in the opposite direction of the driving force. Okay, so very often what we want to find, right, is what is the overall effect that these several forces have on our object. Okay, intuitively, right, just by looking at the diagram, you will be able to guess that since they are pointing in opposite directions, they are going to cancel each other out. Partially, not fully, because the sizes are not the same, right? One is 5,000, one is 3,000, right? This size of the force is basically what we call the magnitude, okay? So net force in this case, you will think, okay, they cancel out partially, right? So after you cancel out this thing, it should be 5,000 minus 3,000 equals to 2,000 newtons. In which direction? In this direction, right? Because the forward driving force towards the left is greater. So after you cancel out the 3,000, you still have 2,000 left pointing to the left. So this is to the left, okay? This is pretty intuitive. The next one is also pretty intuitive, right? We have 7 newtons towards the right, 5 newtons towards the right as well. And so they are in the same direction. They're pushing and pulling, but both towards the right. So what's the overall effect? They kind of add together instead of cancelling out, right? So this is, again, from a very intuitive standpoint, you can kind of from feeling, you already know that it's going to be 12 newtons towards the right. So from a vector's perspective, sometimes what we do is we assign a positive and negative sign to a direction. So for example, in this diagram, right, we can say this direction is positive, this direction is negative. Now, which side is positive, which side is negative is totally up to you. The positive and negative, when you get to the final answer, that positive or negative sign just is an indication of the direction. So given that, let's say we choose right side as positive, then the total force or the resultant force would just be the sum of all the forces. Now we have 3,000 to the right, so this is positive 3,000. Add to 5,000 to the left. Now left side is negative side, right? So 5,000 to the left is actually plus negative 5,000. You see this? Okay, so what is the answer here? We will get negative 2,000, right? Now in this case, when we've chosen to do it this way, this negative sign indicates it's to the left. So if you do it the intuitive way or the strictly mathematical positive and negative sign kind of way, you will still come up to the same conclusion, which is that the overall effect of these two forces acting is 2,000 newtons towards the left. Okay, it's just presented differently. Same here. Well, this one will be very simple, right? Because let's say if we take this positive and this one negative, it will just be plus 5 plus 7. Okay, so total will be plus 12. And this plus indicates that is to the right. Okay, now some of you may be wondering, right, since all this is so intuitive, why do we bother doing all the vector diagrams and so on? Now the reason why is because these are very simple scenarios. Now sometimes we have a slightly more complicated scenario, like for example like this. Now imagine this is the top-down view. We are looking at an aeroplane. Aeroplane is flying this way, right, and it's coming into an airport. Now the air resistance is pushing back on it, right, directly towards the back of the aircraft, but at the same time it's flying through a region where the wind is blowing from the left to right. So if the wind is blowing from the left to right, it's exerting another amount of force, let's say 3,000 newtons on the aircraft. Then intuition doesn't really help us in this case. Well, intuitively we know that, okay, if it's this much force and we are trying to add it to this much force, the sum of it should be somewhere in between these two in direction, right? But exactly pointing where? And exactly how much? Not so intuitive anymore. Okay, so this is where we have to learn how to do vector addition. Okay, so vector addition is actually very simple. What we do is we draw arrows to represent the vectors, in this case the forces. Okay, now these arrows must be drawn to scale in the sense of both the direction must be pointing in the correct direction, as well as the length of the arrow must represent the size of the force. Now length of the arrow represents the size of the force. So that means I should be drawing something like one arrow like this, right, which is 4 units length. Okay, and then I should be drawing another arrow that is 3 units length like this. I'm doing this on the computer screen, so naturally I'm not using a ruler, but for students, you should be drawing this on paper with a ruler, okay? And how we do vector addition, right, is very simple. Now, we are trying to add this downwards arrow with this rightwards arrow, right? Now, I hope none of you just take 4,000 plus 3,000. That doesn't work that way. So what we are supposed to do, right, is we are supposed to take this 3 units arrow or the 4 unit arrow, and we are going to move the arrows around. Now, we move the arrows around without changing the direction of the arrow and without changing the length of the arrow. We are just rearranging them, okay, while maintaining where it's pointing, while maintaining how long it is, okay. So I'm going to move this arrow over here such that the new arrow carry on from where the previous arrow leave off, like this. Now, some of you may have heard of this in school. It's called the tip to tail method. That's one way of calling it. I like to think of it as like each subsequent arrow continuing on from where the previous arrow left off. Okay. Once you've arranged the arrows this way, oh, by the way, in this example, there are only 2 arrows, but the general idea works no matter how many arrows. So let's say if you have 3 arrows, you just take the arrows and then line them at 1, 2, 3, but always continuing on from where you left off. Okay. So once you have these 2 arrows like this, right, this is the original start point, and if you just follow the entire chain of arrows, you end up here. This is the start, this is the end, right? So what you do is you draw a line or you draw an arrow from the start to the end, okay, and you put a double arrow on that. Now this new arrow, this represents the resultant force, and so from the length and the direction of this arrow actually will give us the magnitude and the direction of the resultant force. Okay, so another way of thinking about it would be like, if these 2 forces act together, what is the equivalent one force that will have the same effect? Okay, so that is what we are trying to show here. Okay, this one arrow here has the same effect as these 2 combined. Okay, so bear in mind, it is just a imaginary thing. Like, let's say if we want to combine these 2 into one single one, we will represent it like this. It's not to say that there is a third force that appears. No. Okay, so what you would do then would be to measure the length. What's the length? Okay, you can measure this angle. What's the angle here as well? You would have to measure the length and use that to calculate the force that that length represents. Okay, so what I mean is that, let's say this is 4,000 newtons, right? And I say, okay, 4 cm. I use 4 cm to represent 4,000 newtons. And then 3 cm will represent 3,000 newtons, right? Okay. So we will have to write down the scale here, just to remind ourselves. Basically that 1 cm represents 1,000 newtons. Okay. So then let's say if we measure this length, and this length comes out to be 5 cm. How much force is there here? 5 cm would represent 5,000 newtons of force. Okay, so just to make this point further, I have here a sort of a vector calculator. What is showing here, right, is that these 3 arrows, T, U, V, are 3 different vectors. You can think of this as 3 different forces, right? So W, right, is a computer calculated sum of the 3 forces, right? So now we can have forces, right, that are pointing in any old direction. And as I change these forces, you can see that the overall sum of the 3 forces, W, right, changes as well. Okay, but what I want you to notice especially, right, is that this lining up tip to tail method works. Okay, now it doesn't matter which one goes first. Just as long as you take all the forces that you're trying to add together, you take one by one and line them up, continuing on from where the last one left off. So U starts here, continue on from where U left off, and T goes next. And you can see that W fits very nicely being the one that goes from the original start point to the final end point. Okay, and I'm going to show you also that the order in which I put the arrows doesn't matter as well. Okay, so if I have the green one first, follow it up by the red one, and then follow it up with the blue one again. If I just draw one straight line from the original start point to the final end point, again it fits up with this W. Alright, so I hope you found that helpful and helps you understand vectors a little bit better. And thank you so much for your attention, and I will see you in the next video.